Hi everyone, welcome to Bite Size Med, where we talk about quick, bite-sized concepts and basic medical sciences for study and rapid review. This video is on the compliance of the lungs and the chest wall. Now before I start, I thought I'd let you know that when I studied compliance, it really annoyed me. So I decided to make a video to sort of simplify it the best way that I can, and hopefully it helps someone out there. So let's get started. Now the breathing cycle is pretty straightforward. Air goes in during inspiration and goes out during expiration. During this cycle, there are volume and pressure changes. The change in volume over the change in pressure, that's compliance. So let's quickly go over what these changes are. The volume of air breathed in or out during quiet respiration, that is the tidal volume. That's around 500 ml. Now for this 500 ml to go in or out, the pressures have to change. And air moves along a pressure gradient from high to low. Between the atmosphere and the alveoli is a pressure gradient. Another pressure is in the pleural space. That's the pleural pressure. The pleural pressure is negative at rest at -5 centimeters of water. Alveolar is 0, and all of this is in relation to the atmosphere, which is 0. Now for the tidal volume to enter, the alveolar pressure has to become negative. The diaphragm contracts, the lungs expand, alveolar pressure goes down to -1, and the pleural pressure becomes more negative at -7.5. Air flows from high pressure to low pressure. So now from the atmosphere into the lungs, the tidal volume has entered. At the end of inspiration, the alveolar pressure comes back to 0. For expiration, which is passive, the lungs recoil, and the alveolar pressure becomes positive at +1. So the gradient has reversed, and air leaves the lungs. The pleural pressure goes back up to -5. And the alveolar pressure comes back to 0, and we're at rest again. So at rest, the alveolar pressure is 0, and the pleural pressure is -5. During inspiration, alveolar pressure goes down to -1 and comes back to 0. Pleural pressure goes down to -7.5. During expiration, the alveolar pressure increases to +1 and comes back to 0, and the pleural pressure returns to -5. Now the difference between these two pressures, that's the pressure across the organ, which in this case is the lungs. So it's the transpulmonary pressure. That's alveolar minus pleural pressure. It goes from +5 to +7.5 and back to +5. The change in volume over the change in pressure. So if there's a large change in volume for a small change in pressure, it means it's highly compliant. Versus if a smaller volume needs a higher pressure, that means it's low compliance. So high compliance means the lungs can stretch easier for smaller pressure changes. But the lungs can't just keep stretching. Remember, expiration was passive. It's from recoil. That's elastic recoil. So the elasticity of the lung, that brings it back, just like a rubber band. Once it's stretched, it wants to recoil back. So this is from elastic forces. And one of those forces is in the lung tissue itself. This is an elastic force. So it's from elastin fibers, which are in the connective tissue. When the lung stretches, these fibers stretch too. So they help bring it back to shape again. Another force is in the alveoli. The alveoli have fluid lining them, and they also have air. Between air and fluid, there's an interface. This air-fluid interface results in surface tension. The water molecules at the surface of the fluid try to contract. They try to make the smallest structure, a sphere, and that makes the alveoli more collapsible. So the surface tension is the second elastic force. Now what reduces the surface tension? Surfactant. If surface tension increases elasticity and reduces compliance, surfactant does the opposite. It increases compliance. So if we were to plot pressure against volume, you get that compliance diagram. And the slope of this curve would be the change in volume over the change in pressure. So that's the compliance, that's the formula. So more slope, more compliance. That means a steeper curve means it's more compliant. So this curve is for inspiration and this is for expiration, and they follow different paths. That phenomenon is called hysteresis, and one of the reasons hysteresis happens is because of surface tension that needs to be overcome during inspiration, so that's why the curves are different. Now all of that was for the lung, and the lungs are inside the chest wall, and it has to stretch as well, so that's the chest wall compliance. and the compliance of these two together is lower than any of the individual ones. So this is the lung and this is the chest wall. And at rest, remember, the volume in the lungs is at functional residual capacity. The lungs have a natural tendency to want to collapse, and that's an inward pull. The chest wall wants to expand, and that's an outward pull. These two forces balance each other, and the system is at neutral. When the lungs expand, the volume is getting higher, and a bigger lung wants to recoil more. So its inward pull is stronger than the outward pull of the chest wall. So as a unit, they want to collapse. And that forces the air out. Now reverse it. When the lung is contracted, there's a lower volume, and a smaller lung has lesser recoil, and the chest wall now has a stronger outward pull compared to the lung's inward pull. So as a unit, it wants to expand, and air enters the lungs. So when the unit contracts, it wants to expand, and when it expands, it wants to contract. And that is the compliance of the lungs and the chest wall. If this video helped you, give it a thumbs up, share, and subscribe. Thanks for watching, and I'll see you in the next one.